So for part C of this problem, first off, I'm going to point out again, this is the graph of f, and that's given to me in the problem. They want to know when is h concave up. So when I think of concavity, I think of second derivative. So h double prime of x is what we want to look at. Concave up means that this is positive, that it's greater than 0. So in the previous parts and in the previous video, I worked out that h prime using second FTC was equal to f of x. So if I derive this again, then I get h double prime of x equals f prime of x. So I want this to be bigger than 0. F prime is the slope of this graph. So I want the slope of this graph up here to be greater than 0, which means that it is that the slope is positive. So that means that f is increasing. So this is kind of like the thought process, but this would be like kind of, it says justify your answer, and this kind of work would be great to justify your answer. I think from an AP perspective, if you make this connection and this, you could even make this connection and then go straight to this, I think. But I think it helps to work it out by writing it out like this. So f is increasing. Well, clearly that happens from here to here, and then again from here to here. So my two intervals are from, not increasing at 1. It starts increasing just after 1, and then up until 3 non-inclusively. And then it decreases for a while, and then it starts increasing again at 6, and then goes to 7. So these are my intervals for which h is concave up. So part D, on the actual AP, it didn't use the word absolute, but I added it for us. But there's some clues that it means absolute. Anyway, so the x value of the minimum on h on the interval right here. So since it gives me a closed interval, that tells me that we're looking for the absolute min. But I think that they probably should have included, I would have included, but whatever. We're looking for the absolute minimum on h, which is this integral from 1 to 7. So we already, in part A, figured out that h of 1 was equal to 0. So before I even go there, I should explain why I'm looking at h of 1. So since I'm looking for an absolute min on this interval, I have to consider the endpoints. So I need to consider h of 1, and I need to consider h of 7. The other spot where I should consider is this thing. The other spot that I should consider is this thing right here at x equals 5. But it turns out that I actually don't have to test this value. I'm looking for an absolute min, which means that it's going down and then up. So the derivative is going, remember, this is the derivative of h. h prime is equal to f, and we worked that out in part B. So I want h prime to go from negative to positive for a minimum. So you see here, h prime, which is f, goes from positive right here to negative right there. So that means that this would be a relative max, not a relative min. So I don't have to consider that. I only have to consider the two endpoints. So basically, I need to figure out h prime of 1, and I need to try to figure out h of 1 and h of 7. Whichever one of those is smaller is going to be the absolute min. So you could make this argument in multiple ways, but I'm going to make it in a, I don't know, it might be a more mathy way. So I want to know what is h of 7. So I know h of 1 is 0. So h, remember, is the integral of this graph up here. So what I'm going to do, I know integral is area, so I'm going to call this red, or that green spot right there, I'm going to call that R sub 1 for region sub 1. And I'm going to call its area of R sub 1. Oops. I want to write area of R sub 1. Then this area down here, I'm going to call that R sub 2. And I'm going to call its area R sub 2. So I know that h of 7, this thing right here that I'm looking for, is going to be, well, my starting point is 0, so it's going to be 0 plus the green area, and because that's above the axis, and then the red area is below the axis, so I'm going to get minus the area of that lower bit. So minus area of R sub 2. Now, I think that I would say that this is equal to a, the more mathy way to say it would be, say, this is greater than 0, or you could say equal to a number bigger than 0, or equal to a positive number. And that's because the area of region 1 is clearly larger than the area of R sub 2. So that when I subtract that, it's not going to beat this. So this whole sum of these three things is going to be bigger than 0. So since that's bigger than 0, and I know that h of 1 is 0, then I know that this thing right here, the integral that starts right here, h of 1 is going to give me the smallest value on the interval from 1 to 7. So I say h has absolute min at x equal to 1. I think the key takeaway from this one is just that when we're looking for absolute mins and maxes on a closed interval as opposed to an open one which would have brackets, I have to include the endpoints. So a lot of times on the AP questions, you know, it's not, I don't have to say, oh, this guy's bigger than this guy, right? That argument is sometimes hard to make, and it's not the easiest thing to do to come up with this kind of method right here. But a lot of times you can figure out these areas and add and subtract them appropriately and figure out the endpoints. So key takeaway here, when we have a closed interval and we're looking for absolute mins or maxes, I have to consider the endpoints.